Okay, welcome everybody for this morning session. For the short paper presentations, we will have 5 presenters. The first one will talk about enhancing engagement in token-curated registries via inflationary mechanisms, and it's Gauri Shankar Ramachandran. Please.
Thanks for the introduction. My name is Gauri Shankar Ramachandran. I'm a postdoctoral researcher at the University of Southern California. The presenter who was supposed to give this talk couldn't make it in the last minute, so therefore I'm presenting on Lucy's behalf. So the paper that I'm going to talk about is in the context of token-curated registry. Therefore, I'll start with introducing what do you mean by token-curated registry, or what are token-curated registries in general. So these are nothing but a recommendation list that we are used to in our daily life. When we try to book hotels, probably we go to TripAdvisor and try to look for the rating of a hotel in a given neighborhood, or we sometimes go to apps like Yelp or Google to look at the ratings of a hotel or a place that we want to go and visit. So these are lists maintained by various companies. So in the case of TripAdvisor, they sort of curate the different hotels in a neighborhood and provide you the list. And if you take Google or even Yelp, for example, restaurants and other places are rated by the community members, so you see the ratings. So there is that model. And token-curated registry is sort of a decentralized way of doing creating this recommendation system, wherein we are encouraging the community members to curate the list. So we are providing a platform wherein the community members can actually maintain the quality of this list by rating the items that are already given there. So this concept of TCR was proposed by Mike Golden in 2017. So you can read his blog post on this topic to get into the details of TCR itself. Okay, so the concept sounds interesting. Is it currently being used in any of the applications? Yes. So there is a company called MetaX. They are actually based in Los Angeles. So they have a token-curated registry for managing advertisements. So when we browse the internet today, we notice lots of ads popping up in our web pages. So sometimes we are annoyed with these advertisements, therefore we use ad block services to actually block those advertisements. So what happens is, we are browsing the internet for free, but these advertisements are actually driving the internet, and it sort of provides an incentive for different parties involved in the internet ecosystem. So what AdChain provides is a platform wherein you can find the list of reliable websites where your advertisement can be placed. So you as a company, you want to advertise your product, you don't know which website to choose for your advertisement. You can actually go to this token-curated registry, and you will find a curated list of quality websites where you can post your ad. And if you post your ad through this curated list, your advertisement is guaranteed to get good visibility. So that is sort of the model that this particular company is going for. So in a nutshell, this company is actually creating a curated list of websites where one can actually reliably post the advertisements to reach the end users. So this is one example of TCR, and you can find a number of other use cases of TCR in this space. Okay, everything sounds interesting, but in reality, how this whole token-curated registry works. So we have a number of voters who are actually voting to maintain this quality of the list. And the items are actually submitted to the list by the party who wants to list their item. So this could be, for example, let's say there is a list for maintaining quality universities in a given country. And each university, for example, they can actually go and submit their name to the list, and they can be part of this curated registry. And let's say that you submit one of the university name, then the community members would come into the platform, and then they decide whether this university should be part of this list, whether it's actually a quality and trustworthy, reliable institution that we can actually list in this registry. If the answer is yes, then this university gets added to the list. But if the community members believe that this university is not reliable and trustworthy, they can actually remove this particular institution from the list. So that is how the TCR works. So the role of the voters here is to decide whether a particular item should be part of the list or not. So the way the voting works, let's say that I post an university to the list, and then the community members observe this new item. So there is a period called sort of a registration period. This runs for between 1 day and 1 week, depends on the application that you develop. Within this 1 day or 1 week period, the users or the community members can actually decide whether to challenge this particular entry. Let's say that you don't believe in this particular institution, then you can stake some coins, and you can challenge that, hey, I don't think this is a trustworthy entry in the list. Here is my challenge. Then the community members would start to participate in this system, and a set of community members vote in favor of the challenge. That is, they also believe that this is not a quality institution, or the community may believe that, no, I believe in this institution or this item, therefore I want to accept this particular entry into the TCR. So within this 1 week period or whatever, the community members actually decide whether an entry should be part of the list or not. So that is the whole idea here. So the TCR typically comes with tokens associated with it, and these tokens are what is encouraging the community members to participate, and also they can stake their tokens when they are challenging a particular entry in the item. Therefore, the community members use the tokens that they own to maintain the quality of the list. So that is sort of the model with which TCR operates. So this is a diagram that explains it. So there is a candidate who is applying for an item to be part of the list, and then there are a set of voters who owns the tokens. They decide whether a particular item should be accepted or rejected from the list. Then if the item is accepted, then it gets added to the list. If it's rejected, then the item will not get added to the list. And then the candidate, when they are submitting an item, they put a certain amount of token into TCR. Let's say that I put 1,000 tokens to register my item to the list. If I lose, or if majority of the voters say that, no, this item is not trustworthy, I won't accept this into the list, then the money that the candidate, the tokens that the candidate staked for the item will be distributed to the voters. So that is sort of the way the voters actually gain incentive in the TCR model. Okay, so the problem with the TCRs that we have today is that the token holders, they simply buy the tokens and then they don't actually vote because they are not sure whether they should stake their money, because they don't know whether a particular item is actually really trustworthy or not. They are not good in judging that. Therefore, they are actually not engaging, or they are not participating in this voting system. So there is this free rider problem that we are trying to solve. So the way we learned about this problem is through this ad chain company, and they had a problem that the community was not actually engaging in their TCR platform. Many community members actually owned the tokens, but they were not actually coming forward to curate the list. So they were not participating in the system at all. They were simply buying the tokens and holding it with them. So the solution that we propose here is that increase the tokens for the people that vote or that engage with the TCR list. So what this will do is this will actually reduce or devalue the tokens of the people that don't vote. So that is sort of the inflationary mechanism that we propose in this paper. So I mean, as you can see, that the total number of tokens in the system increases, the amount, as the total number of tokens in the system increases, the amount that is to be staked for a given item is also maintained constant in this model. So the way we evaluated our inflationary mechanism approach is through a simulator that we actually built for this particular project called TCR Sim, which one can actually download and use it. So you can find the entry here. The simulation consists of two key parameters. One is the probability of a token holder being engaged with the TCR list, and also the other is a token holder being informed, which means informed in this context refers to their expertise in a given list. I mean, if it is a list of universities, the token holders have some information about that university, so they are better informed to make a right decision on that particular entry. So that is sort of the simulation parameters that we use. So some of the key results that we got from our work are given here in the graphs. So if you look at the topmost graph, you can see that engaged and disengaged users, the gap between both of them is actually too small. Therefore, whether they engage or not engage, they are actually still gaining some value. So with our inflation model that you see at the bottom, the engaged user's token value is actually increases because he is actively contributing to the quality of the list. Therefore, his token value sort of increases, while the other parties who are not actively engaging, or either they are not fully aware of that particular list, as in they are not fully informed, then they are going to sort of lose the value in this model. And another results that I want to highlight is the average wealth of the user. As you can see, that the engaged user sort of has a higher wealth in this model, while the disengaged and other users sort of loses if they don't participate or if they don't involve in maintaining the quality of the list. So that is sort of the key results that we got from this simulation. So I would like to conclude by saying that this mechanism is actually allowing the community members to actively engage, and they can participate and maintain the quality of the list in the process. And we have proven that through numerical simulations that by giving incentives to the active participants, you can increase the quality. And we also believe that this token would actually allow the active members to engage more, while the passive members are discouraged or they have no incentives to be part of the system if they are not actively maintaining the quality of the list. Yeah, so that concludes my talks. I'll be happy to take some questions here. Yeah.
Thank you very much.
Hi, so I'm just curious whether this token-curated registry thing is essentially the same idea as shelling coin, right? The shelling point voting system where people who go with the majority are rewarded and people who don't are punished. There are a number of general attacks on such voting systems, like the P plus epsilon attack, where you threaten to bribe, essentially, people, and then you can sort of bribe the votes in a direction while not actually spending so much money yourself. Is there any mechanism to prevent that? Because it seems like it's very much in the interest, for example, of malicious advertisers to get the users to vote in the wrong way.
Yeah, it's a very good question. We are not actively, it's not like a social network of users, so therefore you're not fully aware of the participants in the network to actually directly collude with them to bring your entry into the list. Such a problem is possible even if you look at the ad chain platform. Okay, so here is a list of websites, and you still wanted to give some sort of background on the contents on the list. Therefore, they created something like it's like a Twitter like feeds, where the members can actually go and discuss about a given entry, and through this discussion they can come to the conclusion.
But then discussion can also lead to collusion.
Yeah, exactly. So it's not completely avoiding the problem. So there, the company that actually posted an entry can actually recruit a bunch of people to go and flood this discussion panel to actually.
The thing here, actually, the P plus X attack is really interesting because it allows you to very cheaply bribe people. You don't need actual collusion. I think perhaps one interesting solution could be you can make the list adjust only if people consistently vote to certain way.
Let me emphasize that as well. Probably I did not touch that part. There are continuous rounds here. It's not like a one-time process that, a list is created and there you go. It's there. People can actually continuously challenge. Therefore, as a company, you will have to continuously bribe people and find out who is actually curating the list. So it is kind of challenging in the sense, at any point, anyone can actually go and challenge. Even the competitor would actually go and challenge if they see that, no, they are not actually climbing, they are not actually doing what they are claiming to do in reality. Yeah.
Okay, thank you very much. Unfortunately, we are running out of time for more questions, so please ask the speaker in the coffee break. Thank you very much.
Thank you.
I would like to invite the second speaker, Robert Norville, who will be talking about standardizing smart contracts and inferring ARC standards.
Okay, right, that worked. Good morning, everyone. My name's Robert Norville. I'm with the University of Luxembourg. And today I'm going to talk to you about the work we did on trying to define the purpose of Ethereum smart contract on the main chain and whether we can use the function selectors in the bytecode to find candidates for ERCs, which are Ethereum requests for comment. So, why are we doing what we're doing? Well, we started off with the question, what are all the Ethereum smart contracts out there for? Some of them we know if they use an existing ERC or they're very well publicized, but there's a hell of a lot of contracts out there, so we thought maybe some of them we don't know what they're doing. And this led us to a second question. If we don't know what they're all doing, are there things out there that people are doing that we haven't already standardized so that there isn't an ERC for that's being commonly used or variations are being used which would benefit from standardization? So there's a few well-known ERCs, which we, especially ERC20, we make use of in this work to validate. ERC20 being the standard for tokens, so exchanges make heavy use of this, so that one's very useful. Another prevalent one is ERC721, which is the non-fungible tokens. I think the most famous example of this is the CryptoKitties, which famously made millions from its collectible digital cats. A couple of other points I wanted to make. So the standards are often developed kind of reactively. So things are being done, or there's a particular thing people are doing with smart contracts, and then we standardize after it's being done, which makes sense because otherwise we might not know how to standardize. But we're hoping with the work we've done here, it will be possible to make this process a little bit faster so we can spot emerging trends in smart contracts and things like that. And lastly, we make use of the compiled code, which is always available in Ethereum by design, because that's the code we execute on the chain, whereas the source code often isn't. So we focus on the bytecode, the compiled code. So what did we do? Well, we extracted function selectors from the bytecode, since they're always present and available there. We cluster the contracts based on these selectors. We perform a reverse lookup to go back from function selectors to the function name. I'll explain how we do that in a couple of slides as well. And then we use these function names to try and define what our clusters are doing. So do our clusters have purpose? Are they an existing ERC? Excuse me. And if not, can we define any new ERCs? Are there any candidates out there? So, a quick note on function selectors. They're 4-byte identifiers for functions in the bytecode. They come from a hash of the function name, or to be specific, the canonical form of the function name. They're always stored in the bytecode, and because they're generated from a hash, they're deterministic. So the same function always produces the same selector in the bytecode. So we can find these across contracts. Actually, they're also guaranteed to be unique within a contract because it takes the parameters into account, and Ethereum uses overloading, or Solidity uses overloading at least, I should say. And then we extract these function selectors using pattern matching, and then we use these to cluster. and the reverse lookup. This is something that can't be done computationally because it's a fairly solid hash, the KCAC hash. So we use 4byte.directory, which is, I think, a really rather good database. Here, users and interested parties can add a Solidity function name, and the website will create the corresponding selector for this. The result of this is if you search for a selector and it knows what the function name is, it'll give you it. So in our case, with our data set, almost every single selector we had an associated function name. So once we have our clusters, we give the selectors to the 4byte.directory, and we get the names back. A quick note on the data set. Mostly here I wanted to highlight that there's huge replication or duplication of contracts. So we start off with 1.5 million. After we remove the duplicates, we're left with just less than 23,000 contracts. So it looks like a lot of them are being copied again and again, maybe even copied and pasted, or at least there's functionality that's been reused a lot. So we think, again, this is reason to say there might be candidates for ERCs out there. And obviously, because we have almost the majority of the contracts on the chain, ERC20 is present a lot, and we make use of that in clustering. So we cluster with k-means. Because we removed duplicates, each contract is weighted according to the number of duplicates it has while we're clustering. We cluster with increasing values of k, 2, 5, and 9 as we go on, and these highlight different things, and especially once you get to 9, you start getting more what we call candidates for ERCs. The ERC20 contracts, because they're known, they're easy to define, we use these to validate. So if we get a cluster that is exclusively or almost exclusively ERC20 contracts, then we say that we think it's clustering accurately, it's clustering well. So we look for the ERC20 cluster. If that's there and it's strong, then we trust the results of the other clusters. In this presentation and in the paper, we visualize the clustering with single value decompression. So k equals 2, something of a baseline. It doesn't give us any new candidates, obviously, because we only have 2 clusters. But we do find ERC20 with over 90% accuracy. So this was our starting point, a bit of a sanity check. And we said, yes, this makes sense. We have decent accuracy here. Once we get to k equal 5, our candidates for ERCs start emerging. So this one represents 56 contracts in total. At the bottom there, you can see the most common shared function names in this cluster. So almost all of them have things like set sale address, set percentage reduction, change max amount, change owner, things like this. So we think that this is something like a crowd sale, but it appears to have functionality that isn't included in any existing ERC. These function names are not included in any ERC so far. So the idea here with this and the subsequent ones is to kind of draw the community's attention to it. If we can say this is something that's being done or being used in the wild and it's not standardized yet, then maybe this is something the community would like to look at. So this is the first one. Again, we have ERC clustering accuracy of just over 75%, so we think it's clustering fairly well. So moving on to k equals 9, this gives us a further 3 candidates for ERCs. C0 is the second one here. Unfortunately, it's a really small cluster, so it doesn't show up in the visualization, but it is in there. It only represents 7 contracts, but again, none of these functions appear in any other ERC standards, so we think this is something unique, something that hasn't been standardized yet. It's possibly a weaker candidate because it's only 7 contracts, so maybe it's something that's not being used that much. And again, at the bottom there, you can see the function names that resulted from the reverse lookup. As far as we can tell, it's something to do with an agreement schema, because we have multi-sig in there, things like that. So it's some kind of multi-party agreement contract, it appears to be. So C3 is our third candidate. It also appears to be related to funding in some way. Again, we get high ERC accuracy for k equals 9. And the functions at the bottom there suggest that we're looking at how much money is being raised, who's the beneficiary of this money. So again, it's some kind of funding. To me, it looks like possibly charitable cause, but I have no real proof of that, let's say. Interestingly, here we have our first kind of miss in 4-byte directory, let's say. So the second one is, in fact, a function selector that the reverse lookup failed for. So this one wasn't in the 4byte.directory database at the time of writing. If it's been added since, then I can get this easily. But when we did the work, it wasn't there. So that's unfortunately a cache miss. Okay, the fourth and final candidate for ERC represents a really large amount of contracts, so over 124,000. It looks like it relates to ownership and control of contracts. So we have in the reverse lookup in the function names, functions like add owner, change owner, remove owner, change requirements, things like this. So ownership and contract control is nothing new in Ethereum smart contracts. But again, these functions don't appear in any of the existing ERCs. So we think, especially given how many contracts this represents, there's functionality here that isn't standardized yet. So this would be something we would suggest that the community, it might be worth the community looking into. Maybe there's something that we can standardize here in terms of ownership and change of ownership for contracts. So that's what we did in brief. So in conclusion, we found 4 candidates for ERCs that represent varying numbers of contracts in the wild, in the main chain. The first one appears to be for crowd sale. The second one, agreement schema of some kind, because we have the multi-party signature function in there. And one for funding that I speculate might be for charity, but I'm not entirely sure. And the fourth and final one for contract ownership or access control. It's also possible that this could be for ownership of other assets, so it might not be ownership of the contract specifically, it could be ownership of something else that's being stored on chain. I didn't go into them here because of the time limitations, but I think there's, in the paper we have some kind of interesting statistics developers results of the work. For example, sometimes a drop in the accuracy of our ERC20 cluster turns out to be what we've called partial ERC20 implementations. So in these cases, some of the required functions in the standard are missing, but some of the optional functions are still present. So we can say either people implement ERC incorrectly or strangely, or we can say that it's being used in a new way, something like this. But it's not always the case that ERC20 is used as the standard suggests it should be, as far as we can tell. So future work, just quickly, there's a few things we think we could do to improve this work. So at the moment we look purely at transaction volume, which we would say is something like popularity among developers of the contracts. So we weight with number of contracts. I think if we were to use transaction volume as well as either a weight or a modifier, we could say something more interesting. For example, one of our ERC candidates has only 7 contracts, but if these have a huge transaction volume, then we might be able to say this is an emerging trend for ERC standardization. Popularity over time using transaction volume. If there was a really popular contract that isn't standardized, it had a huge transaction volume 2 years ago, it doesn't anymore, maybe this isn't worth standardizing. So we can refine our search, refine our suggestions in doing so. And the last one is kind of a temporal one. Here we just take this 1.5 million contracts, remove duplicates and work with them. So we're not looking at whether these contracts existed before or after relevant ERCs. So if you have ones to do with crowdfunding, things like this, is there an ERC, do they exist before an ERC that has the same topic, or do they exist after it? And again, this would help us refine what is a candidate and what isn't. And very lastly, in terms of the candidate ERC, so we just look at the function names, and I've given you a kind of brief outline of what we think these contracts might be doing based on the function names. If the source code's available or there's GitHub repos, obviously we could use these to give a bit more analysis of exactly what these contracts do and what the subsequent ERC standard would be. So that's it from me. Thank you very much for listening. I'm happy to take any questions you might have.
One quick question.
Thank you for the nice talk first. Have you maybe considered cross-referencing your findings with the Open Zeppelin library, because most of the contracts you found are also there as a template to use for your own smart contracts?
I actually hadn't, but that's interesting. If I understand correctly, that would either some of these things are already there, so
Yeah,
it would be further
exactly.
evidence of a
You have
candidate.
templates for a crowd sale. You have a template for contract ownership there, and yeah, I don't know what will come out if you cross-reference this with your findings.
No, that makes sense. I think potentially that would it could confirm whether what we found is an ERC candidate or not. But I'd be happy to discuss it after if you have a few minutes.
Sure.
Thank you. Oh, and I'm sorry, I don't want to take too much time. I didn't open source the code for this because I'm not quite happy with the state of it. But if anyone is interested, if you talk to me, I'm happy to give you access to the data set and the code we used as well. Thank you.
Thank you very much. All right, thank you. We will move to the third speaker of the morning session. The talk will be about proof of delivery in trustless network, and the speaker name is Kyle Park.
Hi, hello, I'm Kyle Park from Network Defines, and I'd like to introduce our proof of delivery in a trustless network. So the co-authors are Jo Gi-deok and Han Do-kyun from Network Defines, and Kwon Tae-kyung from Seoul National University, and Sang-won Park from Korean University. So the motivation is we want to compensate sender in a trustless network. Since ordinary peers does not have any access to the internet, I mean the routers, each peer cannot confirm or verify a sender's data delivered to a receiver, to each other and also to other peers. So there can be many lies a sender or a receiver can do. First, in a receiver's perspective, it can say like, I haven't received any data, but actually it has received. And also it can claim that I've sent compensation to a sender, but actually it hasn't. Also, in the sender side, it can claim like, I have sent data, but actually it hasn't. And also, it can claim like, I haven't received any compensation from the receiver, but actually it has. So in a trustless network, there is no central entity or superior entity or maybe a global reputation system that can confirm or verify others' claims. So this is the motivation and the baseline of our proof of delivery mechanism. There is a straightforward approach called a micropayment. So under the micropayment mechanism, if the receiver stops compensating or the sender stops sending data, then either party can simply halt the exchange. So under this micropayment approach, a sender or receiver just halts, and there is no remedy for a victim or a punishment for a fraud. So we think this is not enough. If each micropayment is made excessively small to avoid any loss of data or loss of compensation, then the delivery performance will be too poor, since each peer has to wait for a round-trip time to confirm its delivery or provide the others, provide compensation to the other. So so small unit micropayment suffers from poor delivery performance, and also if a micropayment is provided in a large unit, which by definition is not a micropayment, in that case, there will be no penalty to a fraud, which is a non-paying receiver, and there will be no remedy for a victim, which is a non-paid sender. They can just halt the exchange. So under the proof of delivery in a trustless network, a sender proves its delivery in order to compel the receiver to make its payment in a trustless network. So a sender or receiver does not need any aid of centralized entity. Proof of delivery is composed of three logical components. First one is the micropayment, which I've talked earlier, for immediate data transmission, although it suffers from low performance. Second one is trust analysis to boost up or to provide faster transmission to trusted receivers. final one is fraud detection, which is to isolate frauds from the network so you can limit the data delivery to a fraud. Trust analysis and fraud detection are autonomously done by each peer without any aid of centralized or superior entity. Let me go by one. The first one is trust analysis. So a receiver's trustworthiness is analyzed by a sender based on the receiver's payment history recorded on blockchain. So based on blockchain, each sender can reconstruct the payment history of the receiver prior to their transmission. So they can, each senders can have different strategies based on their preference or taste. So if there is Alice and Bob and their payment history is reconstructed like this, then a sender might guess Alice is more trustworthy than Bob because Alice has paid prior data to another sender, but Bob hasn't paid. For example, Bob hasn't paid a data chunk number 1 or 2 of content J. So a sender can assume that Bob is more likely a fraud than Alice. Then a sender can decide that, yeah, I'll believe Alice, but I'll not believe Bob. Oops. So based on the trust window, just like TCP congestion window implemented in the internet, the transport layer of the internet, we implement trust window, which grows in proportion to the trustworthiness of a receiver. So we can enhance the delivery performance. Like if trust window is 3, then a sender does not have to wait for a compensation of 3 data chunks. It can just send 3 data chunks, then it can wait for the compensation for them. In this case, we believe we can boost up the delivery performance of a sender in a receiver. And the other one is a fraud detection and isolation. A fraud, which means a receiver does not compensate a sender, is detected based on probabilistic sequential retrieval and its payment history. And the fraud will be isolated from the network, which means the fraud will not be able to receive any more data from the network, not only from the sender, but also from the other peers. This is a graph shows that each peer is sending and receiving data from each other. And if the peer on top of the figure does not provide any compensation, then the red box shows that the data which is not compensated. Then the other peers will recognize that the top peer is a fraud or likely a fraud. Then the other peers will not provide any data to that red peer. So the red peer is eventually isolated from the network. As I said earlier, each sender can set its strategy, which is implemented by a parameter alpha. So alpha can be set from 0 to 1. So if a sender sets alpha near to 1, then the detection ratio will be low, but the delivery performance will be high. Alternatively, if a sender sets alpha near 0, then the detection ratio will be high, but the speed will be low. So a loss-averse peer or risk-tolerant peer can choose a different alpha values. The effect of fraud detection and isolation is shown when a fraud refuses to pay the reward for the 10th chunk. This is a simulation result. And if a peer refuses to pay for the 10th chunk, then in all cases of alpha, the fraud will be eventually isolated from the network unless it makes proper payment for the 10th chunk. So there are pros and cons of setting high alpha and low alpha. As I said, high alpha provides a better download speed, So it will be good for a risk-tolerant user. And also, if a sender sets low alpha, then although the download speed will be degraded, the fraud detection ratio will be high, and so it will be good for a loss-averse user. Yeah, so that's all for me. Thank you.
Thank you very much. Questions?
Hi. Is it possible to perform a Sybil attack here? I mean, is it possible to create like a lot of fake identities and just slander the reputation of someone saying, you know, it didn't pay, even if he did?
So you mean, so it's easy to make a identity, so
If I have a peer that I don't like, can I create a lot of fake identities, engage in a transfer with this guy, and just say that he didn't pay for my files from all my fake identities? Would it be feasible, or?
I don't think so, because identity is based on hash values, so each hash value is different. So a peer cannot pretend like the other peer.
But I can create as many identities as I want, right?
Right.
With different hashes.
Yeah, with different hashes, yeah.
So can I say from each my fake identity that my peer didn't pay? Can I say it from multiple identities? Is there a protection from that?
Oh, so you mean it's like an attack? You want to make some problems to a certain peer, so you make many identities.
Yes, I want to attack certain peer saying he's not a trustworthy guy.
Oh, no, I don't think that's possible under this algorithm, because so the blockchain says who pays to whom.
Yes.
Right. So blockchain only states that and does not have any information about which data is delivered to whom. Mm-hmm. So the victim under your scenario, there will be no record on the blockchain that the victim has paid or delivered any data. So that victim will not suffer from the reputations or the other connections from the other peers.
Mm. And one more question. So here, your main goal is to perform atomic swap and not to kind of prove the transfer to others, right? So it's only between two peers.
No, we want to verify, or we want to show that the two peers are delivering back and forth, and we want to show that the other peers can also confirm that transmission. So
okay, thank you.
Thank you very much. Any more comments? Questions? Okay, let's thank the speaker again. Our fourth speaker will talk about formal verifications of token economy models, and it's Aleksander Letychevsky.
Hello, I'm Alexander, and I will present our research on the usage of the formal methods and algebraic approach in the verification of the token economy models. So we are the team from the Garuda AI company. It's located in the Netherlands, and we cooperated with the Glushko Institute of Cybernetics and the Kherson State University. This is the team which has had 2 years experience in industrial verification and cooperate with such companies as Motorola and Intel, and we also worked with model-based testing in cybersecurity, algebraic modeling in different subject domains like telecommunication, automotive system, and this team is the followers of the great algebraic school of the Viktor Glushko, and our experience we now continue with the analysis of token economy projects. So these results were obtained after the successful implementation of the number of projects with the healthcare, skill monetization, and the file exchanging service and marketing strategy selection, and the other project where token economy properties were investigated. So the general goal was to create some approach and to create some methods to be confident that to analyze the token economy project, to be confident that it is meet the business expectation. So there are the following tasks. It's how to formulate what property we should check to be sure that the project works properly, how to formulate the token economy, tokenomic objects, how to simulate it, what math and the algebraic methods shall be used for the simulation and proving of this property. So we propose an algebraic approach in tokenomic modeling implemented within the scope of insertion modeling methodology that focuses on the building of model and studying the interaction of agents and environment in a complex distributed multi-agent system. So this is the example of the agents in this Kilonomy project. There are the 7 types of agents. So we have the main agent. It's platform or some kind of platform owner. He created the platform for skill education, online skill and education, and sell the nodes. And nodes owner provide the service, skill education service to the students that perform skill mining. They pay for the education and obtain an award for the successful education. There are good student, best student, excellent student, different kind of students. Too many agents in market the typed or the type students. There are other agents that are interactive, the coaches and managers, which nodes owner were hired by nodes owners. Also, the agents perform different actions. They sell, buy token. There's a token in the system. They invest money, invest token, get revenue, pay fee. Every agent has characterized the type is defined by some set of the typed attributes. These are the set of the attributes of different type: real, symbolic, integer, enumerated. Behavior algebra, it is the mathematical some mathematical methods for the description and of the behavior of the object of the agent, and this behavior algebra we used in the scope of the essential modeling technology. So it was introduced in 1997 by the British scientist David Gilbert and Lichevsky the senior. It is double sorted algebra and is defined on the set of the behaviors and actions, and it defines the operation over these objects. There are the prefixing and the non-deterministic choice, also the number of terminal constants and the approximation relation. So we can define the behavior of the sum agent as the system of equalities. Also, behavioral algebra has two operations over the behavior: is a parallel composition and sequential composition. So this is an example of the creation of token of the behavior of the agent in the token economy project Skilonomy. So you can see in the right side the system of the equalities. So it is presented in a recursive manner. So the main equality, the B, and it is unfolded in other actions and equality. You see the action next month, and then behavior B0, and after that behavior B, and they unfolded another behavior. In the left side you can see the mapping of the algebra to the standard requirement language UCM, use case maps. it is easy to visualize. It's good to visualize the algebra expression into this graphical construction. You can see the action they marked at the cross on the graph, and as a rhombus, it's the behavior which should be unfolded in another graph. Action also has its semantic. It's semantic defined by the triple, the precondition, postcondition, and the process. Precondition and postcondition, there are the formulas in some basic logic language. For token economy analysis is enough to consider the set of formulas of the first order logic of a polynomial arithmetic. And the process component is component for visualization of the scenario of the token economy. So all the semantic of the action is the following: the action is applicable if the precondition is true for concrete case, and the precondition is satisfiable for symbolic case. So what can we do in the scope of the behavioral algebra? First, so when we have the project created of such manner, we can do everything, use all results that we have in behavioral algebra. It's very powerful mathematical, very powerful mathematics. We can use algorithm, theorem, and method that are very developing in the scope of the model checking and formal verification techniques. So we can prove, also this is all can be implemented in the scope of insertion modeling system, which can prove using the its own and the external tools like Microsoft S3 Prover and CVC and other proving and solving system. So we can prove the statements over the agent's environment. For example, this example of the formula, we can use the quantifier, universal quantifier. It's so we can prove the sum statement over the arbitrary number of agents. So, of course, we can we can prove the safety and liveness properties, and in general, this is the resolving of the reachability problem. Is this property reachable or not? If reachable, then we can provide this scenario or behavior in the scope of the given the formalization. So also in token economy, we can analyze that the system is inadmissible event. For example, if you consider the token price should be in the interval that we like to be for successful project. So we can check the persistence of the project under undesirable or malicious action or undesirable change in of external environment. For example, the author of the project, he can assume that there are some there are some dependency token with the cryptocurrency rate, and we can analyze and consider the project due to his assumption, or consider if he assumed some malicious actions of the stakeholders, and he can also analyze to track the behavior of the system. Also, we can use the property that he assumes that projects shall be steady and stable. So what we do, how we can prove, there are some possibility. It is the resolving behavior equation. For example, we can define the sum pattern of the malicious actions. For example, this is the double spending, and to find is it possible, how is it possible in the behavior, and in what case, in which environment. We can also use the symbolic modeling of the behavior of agents. And of course, the algebra, it's not the universal tool for resolving of all problems, so we can face with the exponential explosion. So we use all the power of the model checking, and in this system also I realize some other alternative method for symbolic commodity generation and invariant, different approximation method, and backward symbolic modeling. So it is implied in the platform Garuda IE AI. So you can create your own project, create your own actions. You can launch this project, obtain some charts, and to prove and check this property, create difference agent. So the future work, we also would like to move this technology for modeling of the smart contract. This a little bit complicated than to token economy, and so now we try to create the model of some smart contract, and our future work to translate it to Solidity and to map the result on the Solidity. And the other one is the proving of consensus properties, and we have an experience already with the proving of Prometheus consensus protocol. We found 8 violations and it entailed redesign. Now we work with Ouroboros. It's Cardano consensus algorithm. It's our future work. We will continue. So you can access it's a free platform. You can see the demo, tokenomic, and try to use for analysis of your own tokenomic. And thank you, and contact me if you have interest in it at our side. Thank you.
Thank you very much. Questions? So how difficult is it to put, for example, Cardano consensus protocol into the model to validate the properties? How much effort that requires?
Okay, the biggest effort is to understanding the protocol. I can do it during 1 or 2 days to formalize, but to understand it much harder to create some high-level design. What kind of construct I would like to use in this from the system. So how to simulate this and to prove the property, it's very complicated, and it depends on the property. For example, in the experience of the Prometheus protocol, for example, we didn't prove the finality, for example, but we find the violation. So we don't know. It depends also, but it's interesting that it's suitable for proving of the statement for arbitrary number of nodes. The main feature that we can use the quantifier and to prove the statement. It's of course not all are proved good, but some classes can be recognized.
Okay. Thank you very much. Okay, let's thank the speaker again. And I invite the final speaker for the morning session. And we will hear a talk about Elasticoin, a low-volatility cryptocurrency with proofs of sequential work.
Hi. So the topic of my presentation today is Elasticoin, a low-volatility cryptocurrency with proofs of sequential work. So what makes a currency a useful currency? Generally, we want it to be a medium of exchange, a unit of account, and a store of value. And we want cryptocurrencies, of course, to be a useful currency. Unfortunately, that's not really the case right now. This is mainly because the cryptocurrency prices have really high volatility. So this means they're a poor medium of exchange because the value of the money would change constantly during a transaction. It's a poor unit of account because one Bitcoin means different things today and tomorrow, and you really can't do accounting in terms of Bitcoins. And finally, it's a really poor store of value because you don't know what your stash of Bitcoins will be worth 10 years from now. So this is the price of Bitcoin, and you don't need me to tell you it's really volatile. It goes up and down by orders of magnitude, and that's just really bad. So why are cryptocurrencies so volatile? economically speaking, the main reason is that the supply is completely fixed. So we have a steady amount of Bitcoins mined every block, or Ethers or whatever, and it does not respond to market conditions. Contrast this, for example, to a commodity money like gold, where gold's demand and prices drive gold production, and that stabilizes the prices. Or even just fiat currencies like the US dollar. This means that the price of a cryptocurrency is directly proportional to the demand, and the demand is really volatile because it's driven in large part by expected discounted future demand, which goes up and down based on hypes and panics and such. So generally, a large body of research has been done on this, mostly in stablecoins, which are cryptocurrencies that are pegged to an external asset like the US dollars. There are two different approaches. There are centralized and on-chain stablecoins. So centralized ones are like Tether or TrueUSD. They're very easy to understand. The coins are just IOUs on some bank. This obviously has counterparty risk. What if that bank fails? Maybe it's a fraud. Maybe it gets shut down by regulators. And so this is just centralized. We don't want centralized cryptocurrencies. So this is bad. We also have on-chain stablecoins. This includes Nubits, DAI, etc. We eliminate counterparty risk by replacing the central bank with a smart contract that owns certain assets and tries to use them to back the value of the cryptocurrency. The problem here is that the smart contract cannot actually own US dollars to back the assets. It's a chicken and egg problem. And they have to somehow maintain the peg with other mechanisms that are less stable. And also we need oracles to tell the stablecoin when to sell and buy, which is another centralization risk. So here we can see the price of a on-chain stablecoin called Nubits. As you see, it just suddenly collapsed from a peg of $1 to a few cents because its reserves price would no longer support the currency. And this is generally these on-chain stablecoins have these black swan risks, and that's very undesirable. So our approach is to just be a little less ambitious. We don't really need a very completely stable peg. We just need it to be like gold or wood, to have an elastic supply so that supply would respond to demand, instead of going up and down crazy every time the demand changes. So this would reduce volatility a lot without tying ourselves to another asset. Our general approach is based on fixed minting cost. So essentially, we want to make the cost of creating a coin stable. This is similar to a commodity currency where the cost of mining out a gold nugget out from the ground is stable, and that sort of backs the cost of gold. So this means that increases in market price over cost will be counteracted by greatly increasing supply, and this will deflate any bubbles that form. So how can we incorporate this idea into a cryptocurrency? So the measure of fixed cost we use is actually 1 day of sequential computation on the fastest processor. So essentially, by tying up a day of sequential computation on the fastest processor we have right now, that gives us a coin. This is a really weird metric, but empirically, this has a very stable value. If you rent a single core processor in 1999 and 2019, renting a processor core for a day actually has a very stable price. And this is generally because even though CPUs are getting faster, they're not really generating more value per time, sequentially especially, because software just gets more complicated as well. This sounds really nice, but then how can we implement this? How can we trustlessly track 1 day of sequential computation on the fastest processor? The answer is that we use a cryptographic primitive known as proofs of sequential work. These are a family of algorithms that allow Alice to prove to Bob that she did a certain amount of sequential work, generally hash chaining. So imagine computing a hash, the hash of the hash, the hash of the hash, etc., which can only be computed sequentially. We can actually construct a non-interactive proof of sequential work from related work. The existing work has a lot of interactive proofs of sequential work. We use simple proofs of sequential work by Cohen and Piechak. And we transform it using the well-known Fiat-Shamir heuristic, which transforms any interactive proof protocol to a non-interactive proof protocol to make a protocol where Alice can prove to anybody instead of just Bob that she did sequential work. And this yields two functions, solve and verify. So in solve, we pass in an arbitrary string and a difficulty parameter. Essentially, this does sequential work proportionate to 2 to the n, which is the parameter, starting from chi. And this gives us a proof, a very succinct proof phi that we did this work that we can verify using the function verify in constant time. So now that we have this primitive, we can construct a cryptocurrency minting scheme. So one thing to note here is that even though we're minting these cryptocurrencies through a sort of variant of proof of work, this is unrelated to proof of work consensus. Imagine we're minting this through an ERC20 smart contract, where the consensus is using another currency. So we have two functions here, mapping to the two functions of the proof of sequential work. First, we register a puzzle. This is done simply by broadcasting a transaction containing A, the identity of the minter. Assume that this transaction gets included in block T. Now, once this puzzle is registered, A, the minter, will be able to compute this value chi a, which is the hash of its own identity with the hash of the block in which the puzzle was registered. So the idea is that chi a cannot be computed until the transaction is confirmed in the blockchain. Once that happens, A will start solving the puzzle with a difficulty parameter n, so it can only start the puzzle once the puzzle is registered, and when it finishes solving the puzzle, she can broadcast another transaction to claim a reward R of n. So this essentially, this scheme essentially rewards people for completing a certain amount of sequential work. So the exact reward function is actually where we track the latest computation and all that magic. So how does that work? At any time, the smart contract, so to speak, keeps track of a value Vmax. This represents the speed of the fastest minter we've observed on the blockchain. So every time someone mints some coins, we calculate their V, which basically is how fast they computed the function, which is the amount of work divided by the time it took to solve the puzzle. And then we update Vmax with this value. So when we calculate our reward, we simply calculate it based on how much time would someone running at Vmax have used to complete the work. And we multiply that by a factor V over Vmax that over penalizes slower processors. So this essentially forces everyone to try to be as close as Vmax as possible. This keeps Vmax accurate because everyone tries to be as fast as possible, and also eliminates using cheap computational resources. For example, you stole someone else's phone and ran a few seconds of computation on it, or you're running computation in the background of a busy web server. Since those spare, slow computation cycles generally have very volatile prices, so we want to eliminate them from the market. So this means that the cost of minting closely tracks the cost of running the fastest CPU on the market for a day. So in conclusion, our mechanism, we believe that the best way of reducing coin volatility is not through a central banking pegging mechanism, but to simply increase supply elasticity. And fixing the cost of minting to something that is stable over time is a really good way of making supply elastic. And empirically, sequential time on a current CPU is a very fixed cost. And through the rather new primitive of proof of sequential work, we can actually build a coin on this concept. So that's my presentation. Any questions?
Thank you very much. Questions?
Hello, thank you. I had a question about the energy efficiency. How do you evaluate the energy efficiency of this system? It's like, for me, like you run a proof of work, not a proof of work, but you force them, the validators, to like work to compute. It's
definitely.
like, and if you have a proof of work underlying consensus mechanism, it's like you double the work in overall network.
So Of course, this does waste some energy because the energy used to throw into sequential proof of work is wasted. But compared to a proof of work system like Bitcoin, assume that the blockchain as a whole, let's say, uses proof of stake or a more efficient system. This is a lot more efficient because there's no requirement for people to be mining all the time. It's only when demand increases that people will mint more coins to satisfy the demand. It's very similar to gold mining. People don't actually mine gold constantly at maximum capacity because it's not always profitable to do so. It's only profitable when the demand increases. Yeah.
I was wondering how you propose to set the challenge for each for when one starts mining, because if I can know a challenge in advance, then I can create the illusion that I mined much faster.
Yes, and that is why the challenge is not based on a fixed value, but chi-a, which is hash of a concatenated to ht, which is the hash of the block where you submitted the puzzle. So essentially, you're forced to start working after you notify the blockchain because you don't know from what values you start working from.
You just opened up the door yourself by giving gold as an example. If you look at the gold prices, they are all but stable if you compare it to a fiat currency,
yes.
A decent fiat currency.
Yes, so I would say that this is a rather preliminary work, but still gold is a lot better than Bitcoin. I think gold is not a good example so much, I guess, since its supply is actually not so elastic. The amount of gold on Earth is pretty limited. I would say if you look at the price of a commodity like wood or paper or agricultural products, they're quite a bit more stable than gold, and that's what I'm getting at. I do agree that their price is not as stable as fiat currencies, but I'm not sure that we need it to be that stable. Like, let's say, rather poor quality third world fiat currencies, they're still more usable as money than Bitcoin. And it would be better if we move in that direction anyway. And of course, we can refine this by mechanisms that perhaps, for example, reduce supply when demand decreases, and that may stabilize the price more. But I think this is a great improvement compared to existing issuance mechanisms. Yeah.
Could you run that scheme on a blockchain that is already in place, just implementing it in a smart contract?
Yes, because the proof of sequential work actually doesn't use a lot of fancy crypto. It's just hash trees, honestly. So you can conceivably implement the register and sol functions in an ERC20 contract and sell this stable token on whatever ERC20 exchanges. But it might cost a lot of gas to do this because these functions are not very straightforward to implement in EVM. Yeah.
Why not?
Because they involve, well, the thing here is that verifying these puzzles involves verifying the sort of rather big Merkle tree that is a few kilobytes in size, and that takes up lots of gas. But then if you, for example, it could work because people could just mine in larger batches so that the overhead is smaller. Yeah.
I do not know if this will help you because I'm not too much into this topic, but maybe you want to look into verifiable delay functions.
Yes, I've looked into them as well.
You.
The reason why I chose simple proofs of sequential work is because, first of all, I don't actually need the verifiable part, which the VDFs, the difference between VDFs and non-interactive proofs of sequential work is that VDFs need to be deterministic from a certain result and a certain difficulty parameter and a certain starting point, you always get the same result. I actually don't need this here because we don't use that property, and to achieve that property, VDFs use fancy crypto, so to speak. It uses lots of public key cryptography, and one of the goals I didn't mention is that I want this to be also quantum proof. So we avoid VDFs for that reason. Yeah. And also ASIC proof because it's much easier to write ASICs optimized for computing prime field operations than to just run sequential hashes way faster than CPUs.
All right, thank you very much.